Today we're going to do a thorough review of Euler's formula. Now, Euler's formula comes in many forms. I guess that's why they call it a formula. And so we are going to study the various incarnations of Euler's formula, including the 2x2 matrix form that I prefer. So in this incarnation of Euler's formula, we have some very interesting entities. We have the letter E, which is Euler's number, and we have this letter I, which is the identity of the imaginary numbers, and we have this symbol here, theta, which refers to an angle or a phase, so an angle in a circle or a phase of a wave. And so this is an action-packed formula. There's a lot going on in here that you can't see from looking at these three symbols, but I'm going to map it out for you, and by the end of this video, hopefully you'll have a much more clear understanding of what this means. So first of all, we need to know what E is. Okay, E stands for Euler's number, and Euler's number, put simply, is the base of an exponential function whose rate of growth and decay is always proportionate to the present value. The exponential function e to the x always grows at a rate of e to the x, a feature that is not true of other bases and one that vastly simplifies the algebra surrounding exponents and logarithms. Okay, so you don't actually need to know what this is. I thought for completeness I should read this, but really E is related to exponential growth and decay. Okay, think phi spiral. Okay, so the way you calculate E, so E is an irrational number. It is 2.7182818284590, etc. Okay, and the way you calculate this number is you use this function here. And so this basically says, you can forget about this. It means plug in a value of n and you will produce a value. The bigger the n, the more digits of precision you have of this value of E. And so if you plug in 1 for n, you get the output 2. If you plug in 2 for n, you get the output 2.25. If you plug in 3, you get this. 4, you get this. 5, you get this. And you can see that this number is getting just a tiny bit bigger and bigger and bigger every time. If you put in a gazillion in here, you're going to get probably all these digits here. And so it's getting closer and closer. That's why it's called a limit. The bigger this number is, the closer you are to this limit of this number, this irrational number, which is special. This number has special properties and is related to exponential growth and decay, which is basically what they're saying is this is an expression of what nature does. And this is why E is so important. This is why E is so important because, and this is why it is in this formula, because it has to do with exponential growth and decay, which is what you see in fractal patterns and also what you see in nature. So E is Euler's number and is related to exponential growth and decay. I, of course, is the identity of the imaginary numbers, and I don't think I need to explain that as my last two videos were on this subject. And theta refers to what we commonly call an angle. So theta can either be an angle on a circle, so 0 degrees, 90 degrees, 180, 270, back to 360, or, so that's one cycle, or theta can be a phase in a wave. 0, 90, 180, 270, 360, and of course when you get to 360 you have one complete cycle. And of course, I'm doing this in degrees right now, but for the most part, the scientific community uses radians, and so I will be using radians from now. But you can see the relationship between the circle and the wave, and I will show you a video that shows this a little bit more clearly. So here you can see the relationship between the circle and the wave. Okay, as the circle, as the line goes around, as the dot goes around, the degrees or the radians of the circle, we are in fact going through the phases of the wave. Okay, we are going through the phases of the wave. So the phases of the wave correspond to the angle of the circle. Okay, so the main point I want to make here is that theta does not always correspond to an angle on a Cartesian coordinate system. Okay, sometimes and most often theta corresponds to a phase in a wave. Okay, that's why they call it a wave function. Euler's formula expands into this formula right here. So e to the I times theta is equal to the cosine of theta plus I times the sine of theta. But technically, in my opinion, there should be a little 1 right here and a little 1 right here, just to make sure. So 1 is the identity of the real numbers and I is the identity of the imaginary numbers. And even though you don't write the 1 in here, we still should write it when we're talking about Euler's formula, because we want to make sure we distinguish between the real component and the imaginary component. So 1 is the identity of the real numbers. In other words, every ponderable number, every primordial number times 1 is a real number, and every primordial number multiplied by I is an imaginary number. And so real numbers have a little 1 attached to them, even though you can't see it. And same with the imaginary numbers, only we write the I, now we can see it. So I think it's important when we're writing this formula that we put the 1 in here and we put the 1 in here. So now this formula is even more beautiful because it contains E, it contains the identity of the real numbers, it contains the identity of the imaginary numbers, and it contains a phase angle. So now what we're going to do is a couple of examples. So what we're going to do here is we're going to plug in a value for theta. Okay, so the first one we're going to do is we're going to plug in pi. We're going to plug in pi for theta. And now we're going to write this equation, or this formula, e to the I times pi. Keep in mind that this is just one case. This is just one example of how to use this formula. So in order to answer this question, we'd have to talk a little bit about what pi is. Now I know we all think we know what pi is, and I'm quite sure that most of us do, but just in case there's someone out there that doesn't quite understand pi, I think we should review what pi is all about. Historically, pi is defined as the circumference of a circle divided by the diameter of the circle. When you take the circumference of a circle and divide it by the diameter of the circle, you get this irrational number, 3.141592653, etc., irrational number. Okay, so you get that by dividing the circumference of the circle by the diameter of the circle. And the units in standard units for pi is radians. Now normally radians aren't written into standard unit analysis, but as you may know from my modified unit analysis, radians is a part of the official language. I think it's so interesting how powerful this number is. We have an irrational number, e, relating to the the exponential growth and decay that we often see in nature. We have another irrational number here. We have an imaginary number here. This is really action-packed. So what does this evaluate to? What is e to the I times pi? Okay, it turns out e to the I times pi is equal to -1. Okay, alternatively, you could write e to the I times pi plus 1 equals 0. Sometimes they write this. They call this a beautiful equation because it has, you know, this beautiful e, Euler's number. It has the imaginary identity. It's got this beautiful, another rational number. It's got the identity of the real numbers, and it has 0. So this equation here is often referred to as a beautiful equation because it's got all these interesting characters in the formula. When you expand this formula, you end up with the following. So e to the I times pi is equal to the cosine of pi plus I times the sine of pi. And since pi is a ponderable value, 3.14, etc., we can actually plug that in to this equation. Now this is an equation, okay, and so you'll find that the cosine of pi is equal to -1. The sine of pi is equal to 0, therefore 0 times I equals 0, and you end up with -1. So that is how you can prove that e to the I times pi equals -1. So now we're going to do another example, e to the I times 2 pi. Okay, so, but before we do that, I want to have a closer look at 2 pi, because to me, 2 pi is special and should be grouped together. The 2 and the pi should be grouped together, and I'll explain why. Okay, so what is 2 pi? Well, 2 pi is the circumference of a circle divided by the radius of the circle. Okay, so when you take the circumference of the circle and you divide that by the radius of the circle, you get 2 pi. Now there's a large number of people out there that would actually prefer to use, so this is referred to as tau, T-A-U, tau. So tau is actually equal to 2 pi. So there's a group of people out there that gave this value, 6.28, etc., the label tau, and tau is equal to the circumference of a circle divided by the radius of the circle. And so I just want to tell you one thing. So historically, the reason pi came about is historically, I did some digging, and this is what I think is true based on what I've read. And so it turns out, you know, back in the days when we didn't have, you know, great measuring devices, when all you had was a ruler, it was much easier to measure the diameter of a circle than the radius of a circle, because in order to measure the radius of a circle, you need to know where the center is, and that's not always easy when you don't have the tools to do that. And so historically, it was easier to measure the diameter of a circle, and you could take a string and wrap it around a tree and get the radius of the circle, or the circumference of a circle, and then you get this number pi. So this value is sort of an arbitrary choice. It's based on what was more convenient, I think. And so someone can correct me if I'm wrong on that, but I remember reading something on that, and it makes sense because my husband is a tool maker, and I know he would rather measure the diameter of something than the radius of something. So I want you to close your eyes and imagine a world where everything was written in tau instead of pi. So imagine if we used this number here instead of the digits of pi. Now, I don't want you to actually close your eyes because I want you to actually see what I'm going to say. But so here I have a map of a sine wave, and I have the various different phases written in terms of tau. And so you have 1/4 tau, which is 1 in the sign of 1/4 tau is 1, and that is 1/4 of the complete wave. Okay, and so the next one, 2/4 tau, of course 1/2 tau is 1/2 the cycle, and 3/4 tau is 3/4 the cycle, and 4/4 tau is of course 1 complete cycle. So imagine a world where a quarter of the constant was a quarter of the cycle, and a half of the constant was a half of the cycle, and 3/4 of the constant was 3/4 of the cycle, and 1 complete cycle, of course, is 2 pi or tau. So it's not intuitive to me when things are done in pi. It's not intuitive that pi over 2 is 1/4 cycle. Okay, it's not intuitive, and I'm easily confused, and so this confused me a lot. My brain does not immediately turn pi over 2 into a quarter of a cycle. But if we did everything in tau, obviously a quarter of a cycle, tau is a cycle, and a quarter of a cycle is a quarter of a cycle, a half a cycle is a half a cycle, 3/4 of a cycle is 3/4 of a cycle, and 1 cycle, 4/4 equals 1, is tau. Okay, so I imagine a world where this is true, and so when I rewrite the language of theoretical physics, I am going to use tau instead of pi, and this is going to make a lot more sense, and people are going to have a much easier time, I believe, learning the language. So what are the units of this constant tau? Well, in standard unit analysis, the units of tau would be the same as the units of pi, and it would be radians. But in modified unit analysis, I have both radians and cycles as units in my unit list. And so the units of 2 pi in modified unit analysis is radians per cycle. Okay, so in modified unit analysis, the units of pi are just radians because pi is only half a cycle. Okay, so pi can't have units radians per cycle. Okay, but 2 pi can, because 2 pi is the end of 1 cycle. 2 pi is the completion of the cycle. And so in modified unit analysis, I assign the value to pi, tau, the units of radians per cycle. And so I think it's important to keep the 2 with the pi. I think, obviously, because this corresponds to 1 cycle. And so if in our equations we wrote tau instead of 2 pi, I think we would make less mistakes. We wouldn't be so inclined to divide something else by 2 and separate these two, the 2 and the pi. I think they should stick together unless you can give me some good reason to separate them, and we should be using tau. Okay, and so because the value of tau is 6.28, okay, all the people, the tau supporters out there have given tau a day on June 8th. Okay, June 8th every year, like Pi Day is, March 3.14, March 14th. Tau Day is June 28th, and I think we should all do something special on that day. So e to the I times 2 pi, or alternatively e to the I times tau, evaluates to 1. It is equal to 1. And this is because e to the I times 2 pi, or e to the I times tau, is equal to cosine of 2 pi plus I times the sine of 2 pi. And of course, the cosine of 2 pi is equal to 1. And the sine of 2 pi is equal to 0, so this term evaluates to 0, and you end up with 1. So now we're going to talk about the 2x2 matrix version of Euler's formula. And of course, this is the one I like the best because this is what I actually use in my computer code to make things happen. Okay, and so here is the 2x2 matrix version of Euler's formula. So e to the I times theta is equal to this 2 by 2 matrix. So I think the best way to show you how this works is to do a few examples. Okay, so I'm going to start with the 2 pi example. So what I'm going to do is I'm going to plug 2 pi into this matrix, and I'm going to get out a matrix. Okay, and I drew the graph here so you can see for yourself that I'm doing this correctly. And so you can see that the cosine of 2 pi is 1. Okay, so I put 1 here and here. So the cosine of 2 pi is equal to 1, and I put 1 here and here. And you can see that the sine of 2 pi is 0, and so the sine of 2 pi is 0, and minus sine of 2 pi is 0. And so you end up with the 2 by 2 matrix here. So e to the I times 2 pi is equal to the identity matrix. Okay, in 2 by 2 matrix formalism. So I think this is an important point. As soon as you write a formula that includes I, we're talking about complex numbers. You can't hide the fact that we're talking about complex numbers, okay? This is a complex number, even though these are 0. You can't, even though these are 0, this is still a complex formalism. And so you could say e to the I times 2 pi, okay, you could say e to the I times 2 pi equals 1, but technically that's not correct. Okay, this is actually, I lost my place, sorry. This is technically more correct. Okay, e to the I times 2 pi evaluates to a 2 by 2 matrix with cosine on the forward diagonal with the same sense and sine on the backward diagonal with the opposite sense. And when you plug 2 pi into the equation, you get the identity matrix. That is the correct way of explaining this formula. Any other way is hiding some beautiful features of the 2 by 2 matrix formalism. So let's do another example. Okay, now we're going to do e to the I times pi over 2. Okay, so this is the phase angle, so we're going to plug in the pi over 2 in all of these locations, and we're going to evaluate it. So the cosine of pi over 2, is 0. Okay, the cosine of pi over 2 is 0. And so we're going to plug 0 here and 0 here. Okay, now the sine of pi over 2 is 1. Okay, so the sine of pi over 2 is 1. We put 1 in here. The sine of pi over 2 is 1, but we negate it, so we put 1 minus 1 here. So the e to the I times pi over 2 is equal to what I'm calling I, but I put I in brackets. This is what this is I in complex, in the 2 by 2 matrix complex formalism, this is equal to I. And so you can see how, but again, just because the forward diagonal is 0 doesn't mean the real part disappeared. Okay, there's still a cosine here and a cosine here, and we plugged in a value that made it go to 0. It made the output of the formula of this, component of the formula go to 0. Okay, but that doesn't mean that the real part has disappeared. And this is the mistake I think they make. At least I've heard this over and over and over again. Let's say when you do this one, since imaginary component is 0, it disappears, and you end up with making a statement like, e to the I times 2 pi equals 1. I'm pretty sure that most of the mathematicians and physicists out there that see this equation, e to the I times 2 pi equals 1, I'm pretty sure they don't see a 2 by 2 identity matrix, and this is what it actually is, okay? And e to the I times pi over 2 is equal to this 2 by 2 matrix here. And so this is the literal interpretation of imaginary numbers, okay? So when you turn it into a Cartesian, Okay, when you turn it in, when you're using imaginary numbers in the Cartesian coordinate system, where this is the real and this is the imaginary, that is, I think, a misinterpretation. I think this is not literal. You shouldn't take this literally, because you're going to be making mistakes in interpretation. So I think this is a really important point. Okay, just because the imaginary component is 0 doesn't mean the imaginary component has disappeared, because we still have the sign on the backward diagonal. Okay, this is just the output of this formula. Okay, the formula is still there. Euler's formula is still there, and the real component is still there. The imaginary component is still there, and when the imaginary component is 0 and the real component is non-zero, we still have a complex number. So this was a huge revelation for me, because you hear a lot of talk, especially in quantum mechanics, where they square the wave function to get rid of the imaginary component so that they end up with real and ponderable values. Maybe they don't need to do that. Maybe we're missing 99.999% of the information by doing that, and only that, that only allows us to do things statistically. But maybe if we don't do that, if we keep the imaginary component because it's meaningful, it means something, then maybe we can extract more information. Maybe we can make a better interpretation rather than the statistical square the wave function, so we get a real value that we can, possibly plot on a graph or whatever. So nothing is missing here. We've got the real component and the imaginary component. Nothing disappeared. Technically, this is 0i. This is 1r, and this is 0i. And this is 0r, and this is I. Okay, this is I. So just because we've got zeros here doesn't mean the real component has disappeared. It just means that we are on the 0 point of the real number line. And here we are on the 0 point of the I number line. So I'd like to finish off by giving you an example of how this can be used. Okay, for all intents and purposes, you could practically forget everything that I said up until this point. And if you can understand this formula right here, you don't even need to understand it. I'm going to show you how to apply it. Okay, so if you know this, then you can likely do advanced robotics. Okay, you can use this to do the kinematics on a mechatronic arm, for instance. And so here are the 3 rotations. So if you embed this formalism here into a 3x3 matrix, now a 3x3 matrix is a sub-matrix of a 4x4 matrix, and we refer to this as the rotation matrix. And if you only need to do rotations, you can use this. Or if you have a 4x4 matrix, you can do rotations and translations. But this is the rotation matrix of the 3x3 rotation component of a 4x4 matrix. And when you place this formalism in various parts of the matrix, then you can get rotations about different axes. So this one here would be a rotation about the first axis. Maybe you call that x. And then this one here, you can see it's cos on the forward diagonal, sine, and the same sign and sine on the backward diagonal with different signs. So I'm placing exactly this formalism into this matrix. And so this is a rotation about the x-axis, or the first axis. This is a rotation about the second axis, which is usually the y-axis. And this is a rotation about the third axis, which is the z-axis. So this is a one-to-one correspondence, one-to-one application of the 2x2 matrix of Euler's formula. So I hope this helps you out. It took me a long time myself to really understand this stuff and to really grok all the different aspects of it, but I prefer Euler's formula in this form because I can apply it directly to the kinematics of the robotic devices that I build, that I work on in my medical imaging lab. Okay, so that's all I'm going to say for now. And I hope you're having a good weekend. And of course, as promised, as I always promise, I'll be back.